All right, yeah, my name is Huib Kleinout. I'm a product manager at Google.
And I'm Justin Uberti, and I'm a distinguished engineer at Google.
So yeah, we wanted to go over a few updates on what happened from Google's side in the WebRTC project. So in 2019, we finally got to wrap up WebRTC 1.0, but we also moved the platform forward, took some steps towards NV, and are looking towards new use cases. So putting the last bits of WebRTC 1.0 in place took a little bit more time than we expected, but we got from this. What do you mean? But we got from this napkin design in almost 10 years ago to actually something that's robust and a fantastic ecosystem. There were a few bits that we had to get in place, like perhaps most notably switching towards a standardized SDP format for all the browsers. Both Safari has done that, and Chrome switched early this year. There are now 97% of all the connections that make use of this format. A few still opt out, and if you're still on the Plan B, in the Plan B section, you really have to switch because it's going to be deprecated, but it's working pretty well. Similarly, we moved away from the old statistics API, which included a lot of Google stats, something this, that, or that. And this has been cleaned up, standardized, or deprecated. And now you only have one API to work with to get your quality metrics of WebRTC. Chrome implements more than half of the stats that are spec'd out. And lastly, MDNS. There's been a session about it, excellent session from Philip Henke before. Very important to make sure that we don't offer the ability for fingerprinting through WebRTC. This launch in Chrome, I've seen that it has been very effective in eliminating this problem. And we're working with enterprise admins to resolve complexities where it doesn't work. So yeah, of course, a big thanks to everyone who worked with this. A lot of you in this room, in this audience today, contributed with documentation, testing, experimentation, committing to the platform before we were there. So a big thanks, of course. But there's more. Of course, before we were at 1.0, we already moved forward together. That's how it works. On to the new things. And I just want to mention a few things that we did from Google's side that are quite interesting. So most WebRTC applications either use H.264 or VP8. And of course, AV1 is on the horizon, promising a lot of benefits and goodies, but not there yet. And a great intermediate step is VP9. VP9 is available in Chrome, and we configured it in a configuration that we call KSVC, which is a combination of simulcast and SVC, where the keyframes, they reference each other. And using this configuration, you save almost 40% in aggregate bandwidth. Also, VP9 is more CPU costly for encoding. It's actually cheaper to decode than VP8. So if you have, in a typical conference scenario, you have one stream that you encode and decode many terminals around, then overall the CPU increases almost nothing. Another related improvement for conferencing is that we made tab capture a lot better and easier. So there's an improvement in the UX that makes it easier to share content from tabs, from web browsers, and provide a good experience. The benefit of sharing tabs instead of sharing your whole desktop and conferencing is that it gives a better privacy for the end user. You don't see notifications popping up. And it's more efficient because the browser can shortcut some paths from painting to capturing content. A last highlight I want to mention is that we added multi-channel Opus support. So multi-channel Opus already existed, but it wasn't wired up entirely in WebRTC. Now you can use it both for encoding and decoding, and for playback in surround in Chrome. So you can really provide this cinematic experience just straight from the web browser. We also made some baby steps towards NV. We heard WebAssembly a lot today, how we could possibly use this to ship our custom components, do things that are not possible in the WebRTC stack today, like spatial audio, gaze correction, develop your own codecs, and we made some progress there. So the WebAssembly has gotten more capabilities. The SIMD extensions have been spec'd and will be implemented. The Chrome team started with implementing web transport, and we drafted a proposal for web codecs, how you can interface both hardware codecs and develop your own custom codecs. And this all is going to be tied together, probably with streams. We proposed a way to interact with streams in the peer connection today. So we had some good progress on what the platform is going to look at in the future. And while we extend WebRTC with new capabilities, we also pushed things in terms of performance and reliability. As Tommy from our team mentioned earlier today, the Chrome audio processor has launched in Windows and Mac, and basically resolves any stability problems with audio. Instead of like crashing your whole browser, if something related to audio crashes, the audio process seamlessly restarts, and it removes a lot of the jank in audio itself. And Niels from Mozilla, he mentioned before that they made multiple audio streams 3 times more efficient. Well, we worked on latency in Chrome. So the path from like receiving a video frame at your network socket to displaying it on your monitor, we made it 3 times as fast and a lot more stable than it used to be with VP9, as you can see in this before and after graph. So with WebRTC, like adding these new capabilities, like pushing the limits on performance and latency, it opens a lot up for new use cases that we didn't envision when WebRTC started. From like streaming via VR with spatial audio, doing 4K embedded in devices, remote operation of cars, and building low latency super interactive services. These are new use cases far beyond what we ever imagined in the beginning. And Justin is going to tell you something super exciting that Google has built with it.
Yeah, so I think one of the great things when you look at a platform to understand, how successful is it, is first of all, was it able to realize the goals that it initially set out? Was it able to basically address the problems that were known at the time? Good platforms should do that. But great platforms are able to then address problems that people didn't even know they needed to solve at the time. And as Hype just talked about, there's a number of new things that are coming down in WebRTC. We're going to hear about Phantom Auto and kind of operating vehicles and stuff that, like, when we were thinking back in 2009, 2010, we wanted to just get a video call working in the browser. And the fact you can now drive a vehicle, like, it's incredible. And so some of the other cases that are coming out in terms of low latency interactive services is Google's new cloud gaming service, Stadia. And so these services all have the same sort of needs: high performance, ultra low latency and they build on top of all the work that's kind of gone into the WebRTC platform over the past few years. And so we've been working really closely with the Stadia team on this, and I'll get into the details on some things that we're doing. So cloud gaming have some really unique and stringent demands. First, we need to have ultra-low latency. Second, we need to provide a really smooth, consistent player experience. And lastly, we need to give the developer the tools they need to really realize their artistic vision when it's in this cloud gaming environment. Let's talk about latency first. So why does latency matter? Well, pretty much this. Like, when you take an action in the game, you expect that to happen immediately. So we can't have anything like this happening in Stadia. Now, how are we actually going to do this? Well, here's the kind of like state of the universe today. When you look at video streaming, usually you've got like at least seconds, if not tens of seconds of delay, for existing sort of streaming services. And now some smart people have started using WebRTC for video streaming, and they're able to get into that sub-second delay, and they're doing this for live streaming. They're able to do this for auctions, for things like trivia apps even. And
those are great, but for cloud gaming, we really, really need to drive latency down even further and push the boundaries of WebRTC. So, let's talk about where does the latency come from in typical streaming services? Well, what you've got essentially is you've got the video streamers who are pushing out 5 to 10 second chunks of encoded video to CDNs through a file copy operation, who are then allowing those chunks to be downloaded by browsers over HTTP, TCP, and then those things are then buffered in a pretty large client buffer. And while this guarantees an easy to deploy and scale service and ensures fairly smooth playback, it comes at a cost. And the cost is that you've got pretty significant several seconds, multiple seconds of latency. That's not going to work for cloud gaming. So why? Well, first of all, the server is interactive, not passive. It can't, push a button. It can't take effect in 5 seconds. So we need to basically eliminate buffers everywhere, in the server, in the network, and on the client. And we also need to make sure we avoid packet losses or things that require retransmission, because those will cause the same sort of visual stutters that we're trying to avoid in the first place. Now, here's a diagram of how the actual cloud gaming service looks. And we're at a WebRTC conference, so I'm guessing to many of you, this all looks pretty familiar. Basically, what we've got is a WebRTC call, and for this call, the difference is that one side of it, rather than being a person, is actually a video game running on a server. Now, since we're using WebRTC, this removes a lot of the typical latency you would expect, because WebRTC is already tuned for low latency, and then the latency that, because we removed the buffers, we don't have that same sort of latency that you would have from the typical HTTP streaming service. Now, there's some people out there going to say, but Justin, you've got the speed and light to contend with. How are you ever going to deliver this console-type game experience when you're having to stream this from a data center? Well, it turns out even with the console, there's latency. There's latency in the television or monitor. There's latency in the USB sort of polling system. There's latency even in how data flows through HDMI. So your brain even has latency in it. The human central nervous system typically has a higher latency that's inherent than your round trip time. So this notion of zero latency is a fiction. And really what we're trying to aim for is how do we eliminate any perceptible latency? Well, what does that actually mean? So Stadia team studied this. And it turns out that it really, really differs based on the type of game that you're trying to go after. For RTS games like StarCraft, you can have a fair amount of latency, and the game is totally playable. For third-person avatar games, sports games like FIFA, other sort of fantasy games like Diablo, you can have hundreds of milliseconds of latency. The game is still very, very enjoyable. But the Stadia team wants to make sure they can satisfy, deliver all types of games, including the most latency-sensitive games, which is basically driving and first-person shooters. And in order to get to making sure those games work magically in the service, we need to do a little bit more work. So here's one of the things that we came up with. New congestion control algorithm for the Stadia streamers. And those of you who are familiar with WebRTC congestion control will recognize a bunch of these things already, the concepts that are here. That typical network protocols, or network congestion control protocols, basically work by filling the network until the network starts dropping packets because the buffers have filled up. Well, folks, if that happens, it means we've already stored enough data in the buffer, so we've added a whole bunch of delay. So what we want to do with BBR, or it was already being done in WebRTC, is basically use the transit time as a signal that buffers along the path are filling up. And when the buffers start filling up, we can say, hey, we're sending too fast, and we need to back off. So BBR is using this at scale already in Quick, and it turns out that BBR is actually a really good congestion control protocol that can also be used for Stadia with some special tuning. One of the other things that we're doing here, of course, is also providing a really, really rich data center footprint. We've got over 100 network interconnects and nearly 10,000 edge nodes. And so this basically makes sure that we can deliver the necessary, counting for speed of light, low round trip time for a very, very large number of users. And then lastly, we're building on a pretty large foundation of investments across Google. We've got smart routing within our data centers. We got machine learning for load balancing, load prediction, and then load balancing when a lot of players come online all at the same time. It turns out the gaming happens between a very, very sort of narrow window rather than being spread out, diversely throughout the day. And then there's the other stuff that we've been working on that's Hyde mentioned in the WebRTC stack to minimize the time for actual play out and even sort of capture that occurs like within the browser. So all these things working together allow us to hit what we're shooting for, which is to basically deliver a cloud gaming experience that's as good or better than a local gaming experience, to deliver 4K, 60 FPS, HDR at sub 150 milliseconds end-to-end latency. So, latency is not the only thing that we're trying to optimize for. If that's all we cared about, we just send like a super low resolution stream and just call it a day. We actually have this balance between low latency and also delivering this really visually rich experience that sort of matches what people have come to expect from modern gaming platforms. So there's a bunch of things we can do to try to achieve that. First of all, it's let's figure out how we can actually use the codec that gives us the best sort of bandwidth efficiency and control over the system. Then encoder strategy, how do we make sure that we're using those bits effectively to avoid any sort of visual encoding artifacts? And then lastly, make sure we deal with the fact that for the various client devices that are out there, they each have their own decoders and implementation and possible idiosyncrasies. So we want to make sure we give a lot of control, A, to the developer, and B, within the service to deal with all of that. Now, in order to figure out how we actually address this problem, we first need to figure out what does success mean. And so to figure that out, we need a success metric. And so the Stadia team came up with this MOS metric, which is pretty common across video calling and communications. And through a bunch of subjective training, people playing the service, actually scoring it, able to sort of understand how to train an objective model that basically says, how are we doing? What is the level of visual fidelity that we're actually able to deliver for a gaming session? Now, surprisingly or unsurprisingly, we found out that the actual satisfaction with the gaming playability really corresponds directly to the actual video quality as described in the video MOS model. And so a lot of the work that went into is how do we make sure we make sure that video MOS is high at all times? And so one of the things that comes into is, okay, we see that higher resolution turns into higher perceived video quality, turns into higher perceived playability. So what codec can we get that gives us the highest resolution across different bandwidths? And so we looked at a bunch of things. H.264 has a bunch of hardware support, but VP9 has even much better, over 40% better, as Hype said, bandwidth efficiency. And it turns out that allows us to get to 1080p at a much larger range of bit rates than H.264. And so VP9 is the codec that Stadia has chosen to use for its initial rollout. We also looked at, the objective stats don't tell us the whole story. There's also this sort of question of, well, where do we actually want to display high resolution, high frame rate, and where might we want to do something slightly different? And this graph shows that players who had, when bandwidth was plentiful, preferred 60 FPS, but when bandwidth was restricted, were happier to have a consistent 30 FPS than an intermittent 60 FPS. And so basically, one of the takeaways from this was that optimizing for smoothness of experience above almost everything else turned into a higher playability score and a higher satisfaction from the user. So it turns out that there are a lot of different factors that all sort of work together here in terms of what actually turns into playability. We went through these same sort of tests to understand what was the sort of right set of parameters for all these different variables to figure out how do we deliver the best overall streaming playability experience. One of the things that also came out of this was the notion that the actual game developer should have input into how the game is actually streamed and encoded. And one of the things that is interesting is that there are some perceptual enhancements in terms of the encoding that don't turn into differences on the PSNR scores, but actually turn into a subjectively better, for the MOS scores, improvement. And allowing the game developer to indicate which are maybe complex areas of the game or special scene transitions or other things that are hints, essentially, to the encoder, allows to have a very large increase in the perceived playability score. And then finally, these sort of hints to the encoder also help ensure a smooth player experience and also make sure that the actual encoder is not stressed or overloaded or having to quantize heavily. And then maintaining this consistent bit rate And consistent video quality turns to a better player experience and also turns into a more even number of bytes on the wire, which turns into less packet loss and better quality. So all these little hints to the encoder work together to provide a much better streaming experience. So lastly, we want to make sure the developers have the tools to do this type of fine control. And some of these things we might find are actually interesting to not just Stadia, but other WebRTC applications. So here's one thing. We've got basically our dev portal. You can go in there and run any game, any build of it, and control for both the ingress and egress, packet loss, delay variation, even like you can go and record video, compare what you think is being sent versus what was being received, see what the differences are, see like where you might need to tune the game differently to make sure it works well on different types of networks or in different regions. We've also got this video diff tool where you can go in and see there might be specific areas within the game that have a lot of complexity where you want to have maybe some region of interest or other sort of perceptual improvements. And basically, where does the game interact poorly with the encoder and could benefit from additional hints or custom settings? Finally, here's an interesting one of what we call the smoothness view. And so this is an assessment of the overall sort of smoothness of the stream over the past n seconds. And when you're playing the game and you kind of realize that something that just felt kind of off, you can then pop this up and see, like, was that a problem with the game? Was that a problem with the stream? Was that just a problem with your brain? Like, these are all things that, you can then use to say, like, if you're trying to have this really perfectly smooth experience, why did that actually happen? And I think this is something that probably could be applicable in many other sort of fields of WebRTC today. So these tools are all available. You go to stadia.dev, sign up to be a developer, you get a Chrome extension, you plug that into the browser, you can check all this stuff out. But one thing I just want to take a brief minute to talk about is, is really amazing, as I said in the beginning, to see this all come to life and really benefit from all the work that we and really everyone here in this room has put into the WebRTC ecosystem. Stadia depends on WebRTC, and it gets a lot of value because it can deliver this super high quality experience in any WebRTC browser. And that also means it has access to literally billions of deployed Stadia-ready endpoints. And as I've talked about, the WebRTC platform continues to improve through things like WebAssembly, Web Transport, and this means that Stadia is going to have an even more rich set of tools in the future to really control and deliver an amazing experience. So we're all super excited about where this is going. You'll all be able to get your hands on it next Tuesday, starting at 9 a.m. And to sort of get you all sort of appropriately pumped and ready for it, I'm going to play this. So that's it, folks. Cloud gaming from Google, built on WebRTC.